Hello, students. Has anyone ever ridden a penny farthing? It's one of those weird bicycles that, was invented first. It had a very big wheel for steering and uh, gyroscopic stability. All right, once you got the wheel going, it was easy to stay up on. And then the small wheel was kind of just to keep you from tilting over until you got the big wheel going. And then people rode these, and there was some skill in riding these, and people realized that you could come up with better designs than design a normal bike. But the idea is we're going to set this up where the big wheel is 4 times the radius of the small wheel. And here we have R is half a meter, which seems reasonable in my mind, and the small wheel has R is 12 centimeters, 12.5 centimeters. So we're going to say you start out with the bike moving at 15 meters per second, which means that a point on the tire is moving at 15 meters per second. And the acceleration that it has is going to be minus 6 radians per second squared. We're going to stop the bike again. We're going to slow it down for 8 seconds. And this might end up backing it up, because what happens is you have to pedal this big wheel directly. So you would back pedal it to stop it, and you might end up backing it up for some reason. So we don't know if this will actually come to a rest. We're just going to apply this for 8 seconds and see what happens. What we want to know is, how far does the small wheel turn, and what is its acceleration? All right. So the acceleration's not that hard of a problem. Is if there's a relationship between the sizes of the wheels, then the relationship between the other variables should be the same, we would think. There should be some way of, basically the small wheel has to turn 4 times faster in angular velocity as the big wheel. So what we're going to do is work out how the small wheel is turning relative to the big wheel. So eventually we're trying to get theta here, and we also want alpha here. All right, so both wheels have to accelerate at the same time because they're fixed together. They're part of the same bike. So we can find out the actual acceleration as R alpha for the big wheel. And so it is 0.5 meters times 6 radians per second squared, with a minus sign, is minus 3 meters per second squared. And so now we can go and say, for the small wheel, alpha small is acceleration over R is 3 meters per second squared divided by 0.125 meters. And we'll do some math quickly on the calculator. But what we find is that alpha small is 24 radians per second squared. That's easy enough. And so what's happening here is the tangential velocities are fixed, but the angular velocities aren't. In the same way, the tangential acceleration is fixed. This is a constant as we're doing this acceleration on the big wheel. And so it's going to lead to the ratio of the radiuses. It's going to give you the ratio of the circumferences is 4, and the ratio of the velocities, the angular velocities, is going to be 4, and the ratio of the accelerations is going to be 4. So now we want this theta for the small wheel. And there's a couple ways of going about it. We can get the distance that the wheel has to turn, because essentially it has to stay with the other wheel. So if the whole bike moves a certain distance x, then each wheel rotates the arc length x. So maybe that's a way of attacking it. We'll try to figure out how far it moves. delta x is something. Our tangential velocity, our initial velocity is 15 meters per second. Our final velocity we don't know. Our acceleration is minus 3 meters per second squared. And our time is going to be 8 seconds. So based on these things, we have initial velocity, acceleration, and time. This would be delta x is v initial t plus 1/2 at squared. So 15 meters per second times 8 seconds plus 1/2 minus 3 meters per second times 8 seconds squared. So this thing, 15 times 8 is 120 meters minus, and we'll have 8 squared divided by 2 times 3 is 96 meters. So the total distance the wheel will end up turning, the total displacement is going to be 24 meters. So this is 120 there, minus 96 is 24. So now we can just convert this in terms of the small wheel, right? Theta is delta x over r is 24 meters over 0.125 meters. 1 meter over 1 meter is a radian, and so we'll do 24 divided by 0.125 is 192 radians. Not too bad, right? That's not horrible. Now there's another way of going about this problem. We can go and convert this tangential velocity to the velocity of the small wheel, right? And so let's do that. V initial is r omega, so omega is 15 meters per second divided by 0.125 meters is, it's 15 times 8, is 120 radians per second. And so we have omega is this, omega final we don't know, but we know the acceleration. We're basically going to do the same math. We're going to do theta is omega initial t plus 1/2 alpha t squared. And so we have 120 radians per second times 8 seconds plus 1/2 minus 24 radians per second squared times 8 seconds squared. And so when we do this math, 120 times 8 plus 0.5 times negative 24 times 8 squared is, did I write this backwards? I did. It's 192. 192 radians. We get the same number. Again, this is two different ways of attacking the problem. But this is the thing, is that you may see problems where you're given information that's not about the object you're trying to find information about, but they're related in some way, and you have to figure that out. Let me just make sure this is right. 24 divided by 0.125 is 192. I wrote that backwards. Okay, so it's just kinematics. Probably the thing that will make the most sense for you is to convert everything into your translational variables like this. To always do a translation between problems. Sometimes it's not possible. Like if we don't give you a radius, you can make one up, or you can leave r in as your variable, but you're going to have to be careful when you do that, and it's going to make much more sense to work with angular variables. And sometimes you have to do the conversion. But most of you are going to feel more comfortable doing it this way because you've practiced it. Well, some of you are going to feel equally comfortable because you haven't done it yet. But otherwise, there's different ways of attacking this problem or attacking problems like this. So let's stop there. I hope this makes sense for y'all. Obviously, this is something that comes with practice, and that's why you get a bunch of problems. And if you got questions, feel free to email me. Tomorrow I have to give, so tomorrow is the 8th, I have to give an exam, and that's why I'm on Jigsaw 3 to 6 on the 8th. And if you have questions, 3 to 6 is a good time to bug me. 7 to 9 is horrible. Don't do that. And then we'll see how things go from there. But I needed to get these videos done so that I can grade that exam. So if you've got questions, if you need more examples, email me and let me know. And just realize that it may take me a little time to get to it, especially since I'm grading your work and Radford's work at the same time. It's just the way it is. It's time to go home. It's 6:30. I need to sleep because I've been up all day. Anyway, y'all have a good weekend, okay?